is Risuna. I'll be talking about explainable machine learning in customer chain prediction in the industry of telecommunications. With the rise of competition in telecommunication industries, the marketing strategies for customer chain management are becoming increasingly important. So companies are trying to come up with strategies to reduce customer chain and also boost customer retention. The term customer chain is used to define the loss of clients or customers. So in many global mobile network companies, the annual customer chain rate ranges from 20% to 40%, like hence the innovation of strategies to reduce the rate. So to reduce customer churn and boost customer retention, many companies are employing machine learning to predict the likelihood of a customer switching to another service provider. This approach is proved to be effective and exceeding human performance in predicting customer churn. However, the lack of transparency results in people not deploying the systems or not trusting the predictions made by these models. So we are trying to incorporate explainability in customer chain prediction models. The reason being is that when a user doesn't trust and understand the prediction made by the model, they become reluctant in using the system. So the target of explainable machine learning models is an end user who depends on decision recommendations or actions of the system. Somebody who needs to understand the behavior of the system decisions to fully trust and effectively manage the system itself. So the terms interpretability and explainability are often used interchangeable in some part of the literature, and also in some part of the literature I use as two distinct concepts. So in this work, we'll be using them as two distinct concepts. So interpretability is defined as a degree to which a human can understand the reasoning behind a model decision. So these are models like linear regression, logistic regression using trees. Whereas explainability is defined as a degree to which the internal logic and mechanics of a black box model can be explained in human terms. So looking at related work, these explainability techniques are actually like used in different types of like industrial or like areas. Are often used in like financial areas or healthcare areas. So authors in reference theory, they applied LCM to predict NO2 concentration in time series manner. So they applied SHARP to get an insight as to why the model was making these predictions. So the result of the explainability show that the wind speed, solar radiation, and relative humidity have the greatest influence on the predicting values like the quality of air. And also authors in reference 4, they conducted research to interpret the result of a random forest model for predicting individuals at risk of developing hypertension. So to gain insight to the model predictions, like they applied Lime and Sharp. So for the finding of like this of the explainability, it was that like the two most influential features are age and like metabolic syndrome score. So for instance, like patients who are over the age of 40 who are Black and have a metabolic score less than 12.9 are predicted as high risk. So like this explanation can be then shared with an expert, in this case, a clinician or physician, like so like they can validate that the model is really looking, the model is like it should be looking at the right like features when predicting like these classes. Another study was done by authors in reference 5. So they were trying to predict the credit risk score. They used Lime to get an insight as to why a certain customer was predicted as a high risk of defaulting. So to address or to solve the issue of customer chain prediction, we use three models, which is decision tree, random forest, and LGBM. So to address the explainability issue, we employed Lime and Sharp techniques. So this is for complex classifiers, which are random forest and LGBM in our case. And for the interpretation of the decision trees given by the tree decomposition, showing the rules that led to a particular prediction. So the motivation behind choosing Lime and Sharp is that Lime performed fidelity measure, which provide us with a strong indication of how dependable the model, the explainable model is at explaining the black box predictions of a certain instance. And what else Sharp give us mathematical guarantees of the accuracy and consistency of explanations, as well as guarantee of a fair distribution of the contribution from each variable. So a LIME is defined as an explainable technique that provides local explanation using local surrogate models to approximate the predictions of the underlying black box models. So the idea behind LIME is that, like, suppose you have a black box model of any kind that takes input data points and outputs the predictions. So you can query the black box as often as you want with the input data. So your objective here becomes understanding why the machine learning model made a certain prediction. Then what Lambda is like, it looks at what happens to the predictions of your black box model when you feed it variations of data. So LIME generates a new data set consisting of perturbated samples and the corresponding predictions of the black box model. So on this new data set, LIME and then like trains an interpretable model. So that learned interpretable model is a good approximation of the machine learning model predictions locally. So here's an example. We have our random forest, and we have a particular instance of an observation, right? And the prediction for that particular instance. So these are the given features or variables for that certain instance. So what our LIME explainer does, it gives us an explanation where the model was focusing on when making that certain prediction. For instance, for this instance, the predicted variable is Churn, right? So it gives you the features that contributed to that prediction. So this information can be shared with the customer manager who can actually validate, okay, yeah, actually from our expert knowledge, we can verify that this information actually contributes to high rates of churning. So SHARP, the goal of SHARP technique is to provide an explanation for the prediction of an instance X by calculating the contribution of each feature. So the input for SHARP is a chain model F and a specific instance X, right? The output of SHARP is an explanation for every feature. So we get the contribution of these features to the model score F of X. So this contribution is additive contribution, meaning that we add the contribution of each feature to the model score. So here's an example below. We have our black box model and the Churn rate score, which is at 0.7. Why is that, right? So on our right, we give an explanation, explanation why the score is that. So you can see that the tenure month has a positive contribution of 0.5. So you check the contribution of each feature towards the score. So those contributions are then added, then we give our model score, which is 0.7. So looking at the data set and the pre-processing step, the data set used for this paper or for this manuscript is from the customer data set based on a fictional telecommunication company that provides phone services and internet services. So this data set was actually created by IBM. So we have the data set contains 7,000 for the 3 instances with 33 features. And the distribution of our classes, it's well in balance. We have for tuning, we have 27%, and for non-tuning, we have 74%. So as part of our pre-processing, we remove attributes that were leaky and had a single category. And we, to balance our classes, we perform random undersampling. So after all those steps, we're left with 3,738 instances. So out of 33 variables, we only use 18. So we use attributes like city, gender, senior citizen, independence, right? To train our models. So before we actually move to explainability, we have to give the model performance, our model performance, right? So you can see the LGBM achieve an AUC score of 0.87, implying that the model has 87% probability of separating the churning customer from the non-churning customers. So telecommunication service providers they often prioritize customer retention over acquiring new customers. So this is because it is more expensive to acquire new customer than to retain an old one. So in this case, we want to have minimal false negatives. So our LGBM has the minimal false negatives compared to the other models, and also it has like the lowest misclassification rate compared to the other models. So here's the summary of our interpretation of like decision tree. So we have like some 5 simple rules that leads to for like 5 simple rules like for customers with churn risk. So the rule number 1 is that if a customer does not have a contract with the service, they are classified as like a high risk. And rule number 2 is that like if a customer does not have a contract and no information about the online security is recorded, that customer is classified as high risk. Rule number 3 is that like if a customer does not have a contract, no information about online security is recorded, and they do not have dependents, that customer is classified as high risk of churning. Rule number 4 is that like if a customer does not have a contract, no information about online security is recorded, they do not have dependents, and they have not been with the company for more than a month, that customer is classified as high risk. Rule number 5 is that like if a customer does not have a contract, no information about online security is recorded, they do not have dependents, they have not been with the company for more than a month, and their monthly charges are less than 0.283 USD, that customer is definitely classified as churn risk. So looking at the result for our LIME technique, the figure above is generated using random forest, the below is generated using LGBM. So like both the figures present example of a customer index to like, so if this instance or like this observation, the actual observation for that class, the actual class for this observation is actually like churning, and the model prediction for this specific observation is also like churning. So so this is like a true positive case, right? So for both the model, we can see that a customer, like sorry, like a customer, sorry. Oh no, sorry. The result for the interpretation of the customer churn show that the dependence, contract, online security, tech support are the most significant drivers to the prediction value, right? So the 4 top features push the prediction towards like churning. So we can say that a customer who has no dependence on a month-to-month contract, has no online security, no tech support, has a high risk of churning, right? So an effective way to retain customers would be like in this case would be to make sure that the customers like sign an annual or a 2 years contract. And also like when acquiring new clients, the company should target clients who have dependents and like develop strategies like to retain customers with the current customers with no dependents. So looking at the results of our SHARP, so we can see that like the above figure was generated using random forest, the below generated using LGBM. So the pink or the red like stripes, like those are actually positive contributions, whereas the blue are negative contributions, right? So we can see the 10-year month, the total charges, the contract, and the dependents actually have a positive contribution towards the predicted value, right? So like they push the prediction to churning, and like for both the models, online security like has a high negative contribution towards the prediction. So looking at the conclusions and the future work, with customers who are, so we can say that like from the result, customers who are not on a contract, have no dependents, and have less change a month with the company, they can easily migrate from one service provider to another. And also like when using LIME for both random forest and LGBM, it is like that the churn risk in customers who are on the churn risk is in customers who are on month-to-month contract, who do not have online security, who do not have any dependents, and have like a change a month of 10, right? So the company can make an informed decision, know exactly what to look for in order to prevent or stop like customer churn. So for future work will be to expand this work into deep learning, and also to add counterfactual explainability, right? So what it does, like it generates counterfactual examples, like to actually giving it an insight what kind of changes can be made from the inputs to change a certain prediction to the desired one. For in this case, our prediction will be like customer churning, right? So how can we actually change the input, like to change the prediction to the customer not churning? So these are the references that I use for. These are some of the references that I use in this paper. Thank you. Now we'll be taking questions and answering. Thank you.